In this video, we're going to change tactics a little bit, and we're going to talk about moving around a graph or traveling around a graph. And this is a topic that I really wish I could skip. It's a lot of terminology, terms of very similar situations, but it's going to turn out as we do more interesting problems with graph theory that this is going to be important. And so I tried to skip it, but we can't. So let's get to it. Okay, so here are some of our terms. A walk from vertex V to W is a finite alternating sequence of adjacent vertices and edges of G. So if we call this V and we call this W, a walk is going to be any route where we start at V and we go around the graph in different ways, maybe even repeating ourselves to get there. Pretty much any way of traversing this graph can be called a walk. Okay, and a walk is sort of the default. How do I move from one vertex to another? Well, I can imagine walking along a graph. Imagine you're this little person, and you're going to walk along the graph. Like that. Okay, so that's a walk. Now, I'm going to erase this. And we're going to do a trail from V to W. Is a little bit more specific. It does not contain a repeated edge. So in the previous walk, walks can have repeating edges. Walks can have anything. So, but a trail cannot. So a trail might be something like this. Oh, no, we have a repeating edge. Oh, we can go this way and then back and down there. Of course, it's a very complicated trail. It's not a straightforward trail. A straightforward trail could be something along the lines of from here, there, actually, better one. From here to there to there. All right, so that's the most straightforward, that's the shortest trail we can come up with, or walk. And finally, notice that trails can have repeat vertices. So we can, I think my first trail had that, where we started here, and we can go through the same vertex a couple of times. So we can go there, we can go there. We just can't repeat edges. We can go there. I can come here, I can go there, and there. So that's a totally legitimate trail. This can have repeat edges, or can have repeat vertices. A path is a trail that does not contain a repeated vertex. So it is a trail, meaning no repeated edges, but it adds the new restriction that it does not contain repeated vertices. Right? So this one is, V and W. A path is more or less a fairly straightforward way to go. You cannot go back over your own path in any way. Okay, a couple more. A circuit is a walk. Now remember what that means. That means it can repeat vertices, you can repeat edges. It's a walk that starts and ends at the same vertex. It contains at least one edge and does not contain a repeated edge. Oh, well, so this does not contain a repeated edge. Makes it seem like that should be a trail, not a walk. But this is the definition given in the text. So a circuit, we start somewhere and then we walk around the, let me see if I can do this. Trying to cause a repeat vertex. Here we go. Right. So that is a circuit. We repeated this vertex, but that's okay. That's allowed in the definition of a circuit. However, a simple circuit is it's kind of like the path on the previous page. You can't have any repeated vertices. You can't have any repeated edges. It's just nice and clean. So a circuit, and we can start at any vertex. There's no reason I keep starting there. Start down here. So a simple circuit might be something like this. Right? No vertices were repeated, no edges were repeated. That's a nice simple circuit. So let's do some examples. I have a graph over here with the vertices and edges labeled. It probably would have been a bit easier with where the edge is not labeled, but they are. So let's start, and we're just going to walk through here one at a time. So we're supposed to start at V1, and then we do E1, Here, maybe we underline these instead of mark them off. Then we do V4, E3, V5, E5, V3, E8, V7, E7, V8. So, you can ask, what is this? Is it a walk, a trail, a path, a circuit, a simple circuit? It can be more than one. And in fact, in this case, it is a walk, it is a trail because there's no repeated edges, and it's a path because there's no repeated vertices. It is not a circuit or a simple circuit because we don't start and end at the same place. Okay. And another one. Same graph. We start at V1 again. Then we do E1, V4, E3, V5, E5, V3, E4, V2, E2, and back to E1. So you might wonder, what is this? Well, pretty much everything is a walk. It is a trail because we don't repeat any edges twice. It is not a path. And that's because we repeat that start vertex twice. So it's not a path. It is, however, a simple circuit, which means it's also a circuit. And you might wonder, if this is really necessary to write it out this way. This would be equivalent to saying V1, V4, V5, V3, V2, V1. I mean, you don't have to give the edges, but you know that if you start at one vertex and you go to the next one, you're going to need to take one of the edge that goes between them. Now, if you have a multi-graph with multiple parallel edges, that's when this format here, noting the edges, is especially important. And another. We have V1, E1, V4, E3, V5, E5, V3, E9, V6, back over E9 to V3, and then from there we're going to take E8 to V7. So in this scenario we had we have a repeated vertex and a repeated edge, and so that's going to affect this. And in fact, it's a walk because pretty much everything is a walk, but it's not a trail because we have the repeated edges. It's not a path because we have repeated vertices. It's not a circuit because it doesn't start or end at the same point. Same reason for that one. Okay, so this is just a walk. Okay, last example, I promise. So again, we start at V1. There's no reason I'm starting at V1. It's just convenient. V1, E1, V4, E3, V5, E5. Whoa, it's a little straighter. V3, E8. V7, E7, V8, E6 to V5. So this is sort of, this one's we've seen twice. So this is, everything is a walk. So this is a walk. Is it a trail? Well, we don't repeat any edges twice, so yeah, this is a trail. Is it a path? No, and it's because we see that vertex twice, so it's not a path. It's not a circuit because it doesn't start and end at the same point, and same thing with simple circuit. Okay, so you can see it's fairly straightforward to walk through these. I really recommend underlining or crossing out the terms that you've covered. Otherwise, it's easy to kind of get confused as to what you've done or not. So in a previous video, we talked a little bit about connected graphs and graphs that were disconnected. Here we're going to give the formal definitions. We say that two vertices, V and W, are connected if and only if there is a walk from V to W. Right? It doesn't matter if we do the same edges over and over again or the same vertices over and over again. If I can get from one to the other somehow, then they're connected. And we say a graph is connected if and only if, for all vertices V and W in the graph, there exists a walk from V to W. Right? And hopefully that makes sense. It's just saying the whole graph is connected if for every pair of vertices we can get from one to the other. And these are all unconnected or undirected graphs. That's not necessarily the case in a directed graph. Okay, and we say a graph H has a connected component, is a connected component of G, if and only if H is a subgraph of G, and H is connected. Right? So looking at this graph down here, this is not a connected graph. Because we have this little loner over here. However, this part is a connected component.